Hello everyone and welcome to our presentation. We are Group 6 and today we'll be presenting mathematical modeling of tea drying. We hope you enjoy.
The journey and process behind a cup of tea is very long and it begins much before you begin to steep your favorite drink. The growing and processing of tea is an art requiring much care and detail. Tea leaves are dried after harvesting, but there is always a chance of uncertainty in the observational data and in the calculated data, which can be estimated by use of mathematical modeling. Furthermore, assessment of mathematical models is essential to know how they simulate the important features of natural system. So in this study, efficacy of different models is tested on basis of three main parameters, namely root mean square error, reduced chi-square, and coefficient of determination. The model whose results were found to be in close proximity to the experimental results was considered to be accurate out of all. Talking about the introduction, tea is of paramount importance due to myriad of properties and associated benefits. Approximately 1500 diverse varieties of teas are produced worldwide based on climatic conditions, texture of soil, and methodology. Overall processing involves several unit operations, but drying is one of the most important one as it plays a crucial role in preservation and shelf life extension. For predicting drying behavior, explanation and representation of drying kinetics is must. Mostly non-linear regression analysis is utilized by researchers, but in our study, parameters used are coefficient of determination, chi-square, and root mean square error.
The second most consumed beverage in the world after water is tea, which brings with it a pleasant astringent taste. Black tea is the most consumed among all kinds of well known tea, which are green tea, oolong tea. Two kinds of processing methods are known for black tea, which is the orthodox method and the CCT method. First, the tea shoots are plucked and withered. For the orthodox method, the tea leaves are rolled, sifted again and again, and finally fermented, then fed to drying, and we get the orthodox black tea. For the CTC method, after withering of the leaves, it is macerated, then fed to fermentation, and followed by drying. Rolling and maceration is the mechanical process for conversion of enzymes or flavonols. Fermentation is the process of conversion of tea phenolics in the processing of black tea. Now let's come to the drying of tea. Drying is the phase in which moisture is removed from the fermented tea leaf by application of heat. The enzyme activities and oxidation comes to a halt in this process, which leads us to extend the shelf life and facilitate in handling and transportation of the tea. Now, talking about the taste of the tea, the TFs and TRs are also responsible for the taste of the tea. The taste is accentuated during the drying process because all of the unwanted compounds are removed during the firing of tea. TF gives it a fresh and brisk taste. Therefore, more the concentration of TF, better is the quality of tea. Flavor of tea reduces when it is heated above 130 degrees Celsius, but it is observed to increase up to 100 degrees Celsius. Now, talking about the types of dryers which are used for firing of tea, most commonly used dryers are fluid dryers and endless chain pressure dryers for the drying of tea. Numerous works have also been conducted to determine the effect of different drying methods like microwave, far infrared, and freeze drying on the quality of the tea. But these two types of dryer are the most commonly used. When talking about solar drying of tea, it can decrease our energy requirement by a large amount. Therefore, hence, moisture content has a remarkable effect on the quality and shelf life of tea. Moreover, it has grave effects on physical, structural, chemical, and nutritional properties of tea, making it one of the most important operations in the processing.
Now, the mathematical modeling of the black tea. The above section point toward the fact that moisture content has a reasonable influence on the quality of tea, and thus mathematical modeling is necessary to study the drying kinetics of tea. The models which are developed over time are used to develop new drying systems or to improve the existing drying process. Some of the models include the Lewis model. It is a commonly used model for the drying. In the Lewis model, which is analogous to the Newton's law of cooling, the drying rate is proportional to the difference between the actual and equilibrium moisture content. This equation considers the internal resistance to be negligible and only the surface resistance to be taken into account. Another equation that is used widely for thin layer drying is the Page equation, which is the modification of Lewis model by introducing a dimensionless empirical constant n to the time term such that it gives better result for rate of the moisture loss. So this is explanation of Page model. The Henderson and Pebys model. This model uses the first term of general series solution of Fick's law of diffusion. It is quite successful to predict drying rate at the beginning of drying process but becomes less accurate for last stages of drying. In the given expression, A is the dimensionless constant which gives the indication of the shape. Two-term exponential model. This model consists of the first two terms of solution of Fick's law of diffusion. It was modified by reducing the constant number and organizing the second exponential term. Now the logarithmic model. This model is in the logarithmic form of Henderson and Pebys equation in addition to an empirical term and was applied for drying of pineapple. In the given expression of moisture ratio, C is the empirical constant. The Verma et al. Model. This model applied for rice is a modification of two-term exponential model by adding an empirical constant. Now, the diffusion approximation model. By rearranging the Verma et al. Model to separate the drying constant K from G, the new model is obtained with the expression of moisture ratio, and this equation is diffusion approximation model. The Midili et al. Model. This model consists of a linear and an exponential term which relates the moisture ratio with drying time. This model is similar to Henderson and Pebys model with an added empirical term that includes T. Now the next model is Wang and Singh model, in which a new quadratic equation was used to fit the single layer drying of rough rice proposed by Wang and Singh. Next model, Sharaf-Eldin et al. Model, is a new model which was presented for drying of ear corn by Sharaf-Eldin. The two-term model. In the expression of two-term model, the first two terms of the solution of Fick's law of diffusion are used for overcoming the shortcomings of Henderson and Pebys model, where A, B are known as model constant and indicate shape, and K1 and K2 are the drying constants. It was used successfully for this thin layer drying of black tea. Sura et model. Similar to the Page's model, this equation was used for thin layer drying of rough rice.
Several literatures have indicated there are lots of problems in tea drying. Till date, in most of the tea industries, two types of dryers are in use, namely endless chain pressure dryer and fluidic bed dryer. In these methods, tea particles are subjected to a very high drying temperature of around 100 to 150 degrees Celsius. During the process, due to high drying temperature, most of the tea quality attributes are degraded. Research indicated that it is desirable to maintain the optimum ratio of thiaflavins and thiarubigins 1:10 to get the overall best effect in terms of aroma, taste, colors like yellowness index, redness index, antioxidants, and other properties. One of the main purposes of tea drying is to arrest the enzymatic reaction, to stop the oxidation, also called fermentation. So, drying temperature is to be monitored in such a way that it is able to inactivate the enzymes like peroxidase and polyphenol oxidase. Also, in the meantime, quality degradation due to high temperature has to be controlled. Drying is a very energy-intensive unit operation, which must be controlled carefully in order to minimize the energy consumption. Considering these factors, taking into account climate change, sustainability, and environmental change, this study focuses on the development of vacuum-assisted solar drying of tea and mathematical modeling of thin layer drying characteristics of CTC black tea. Materials and methods. Regarding the material selection, in this study, we considered Camellia sinensis shoots consisting of a terminal bud with 2 leaves of variety Tokli vegetative 25. The harvested leaves, before it is taken for the drying experiment, undergone several operations such as withering, maceration, followed by fermentation. The leaves that has been macerated and fermented, which is also called as dul, were taken and considered for the drying experiment. Drying experiments were carried out using a vacuum-assisted solar dryer. The drying experiments were performed at a vacuum level of 400, 500, and 600 mm mercury at a constant loading rate of 1 kg dry solid per meter square. The drying system consists of 2 flat plates solar collectors, drying chamber, vacuum release valve, vacuum gauge, storage tank, drying chamber glass cover, water ring vacuum pump, several riser pipes, and piping system. The drying system works on thermosiphonic effect. The cold inlet water is heated up at the collector plates and moved into the hot water storage tank due to density difference. That is natural circulation. From the storage tank, the hot water is circulated through the drying plate. The transparent glass cover provided at the top of the drying chamber allows direct solar radiation into the drying chamber. In this drying system, the necessary vacuum level were maintained using vacuum release valve. For mathematical modeling of drying, nonlinear regression analysis of the drying data was performed by using a software, Origin Pro. Drying data were fitted into various drying models, as shown in Table 1. The best fit model was selected based on higher value of R-square and lesser value of root mean square error and reduced chi-square. Results. It was found that page model has the highest value of R-square and lowest value of root mean square error and chi-square in all the drying conditions, that is 400, 500, and 600 mm mercury at the constant loading rate of 1 kg dried solid per meter square. It was observed the value of R square, root mean square error, and reduced chi-square were 0.99001, 0.03606, and 0.0013 respectively for 400 mm mercury. Similarly, at 500 and 600 mm mercury, it was found to be 0.001 0.99625, 0.02253, 0.0005074, and 0.99794, 0.01676, and 0.000281 respectively. Figure 2 shows the comparison of experimental moisture ratio and the moisture ratio predicted by page model at 400 ml mercury vacuum level. Figure 3 represents the variation of moisture ratio with time at 400 ml mercury with a loading rate of 1 kg dried solid per meter square, which shows the experimental values versus predicted by page model. Similarly, figures 4, 5, 6, and 7 represents the observation of drying experiments at 500 and 600 ml mercury at 1 kg dry solid per meter square. It was observed that the experimental moisture ratio were in close agreement with those predicted from the page model, with R-square value greater than 0.99. The time taken to accomplish the drying process, that is, to bring down the moisture content to a predetermined level of 3 to 4% wet basis, where 230, 190, and 160 minutes for 400, 500, and 600 ml mercury respectively. As evident, the drying rate accelerates with the increase of the vacuum level. The outcomes of this study would help in designing of drying equipment, improve drying efficiency, enhance the quality of end product, appropriate selection of drying conditions, and reduce the cost of production.
In conclusion, drying methods have changed drastically throughout the course of history. Today, we study the effects of vacuum-assisted solar drying on black tea leaves. Our group tested the various available mathematical models to determine which is best suited for this drying procedure. Using the three main parameters discussed in our presentation, we have concluded that the page model is best suited as the predicted results most accurately describe the experimental data. Improving the drying process will lead to a better quality product for the consumers and a reduction in energy consumed, which will benefit the planet. Thank you.